In this video, we cover the last bit of content about the periodicity of the chemical properties of the elements in group 3, and we're going to do the following. We're going to describe and explain the reactions of the chlorides with water. It's the only thing that we still have to do. The other two learning outcomes here: interpret the variations and trends in B, C, D, and E. So B, C, and D refer to the trends and variations that we've covered in previous lessons. We have to explain these in terms of bonding and electronegativity, and we have done that as we've worked through the different trends. And then lastly, you should be able to suggest the types of chemical bonding present in chlorides and oxides if they give you certain observations of their chemical and physical properties. So based on what you've seen in the previous few lessons, if they give you certain observations, you should be able to suggest the identity of some unknown chlorides or unknown oxides. So we will consider the behavior of the following chlorides with water: sodium chloride, magnesium chloride, aluminium trichloride, which generally exist as the dimer Al6Cl6, and then silicon tetrachloride and phosphorus pentachloride. The first chloride we'll consider is sodium chloride, and I'm not going to show a video clip for this particular interaction with water because it doesn't really involve a chemical reaction. You're not going to make any specific observations which you're not aware of already. Sodium chloride, we know, is a white solid, and when we add sodium chloride, common table salt, to water, what is going to happen? The sodium chloride will dissolve. Okay, so that white solid will disappear. What will the resulted solution look like? It's going to form a colorless solution. So there's nothing new in this interaction with water. To show this dissolving process taking place, you can write your equation as follows. So sodium chloride, that white solid, so we indicate with an S that sodium chloride is a solid. To indicate that it's dissolving in water, you can add plus AQ. And when we add sodium chloride to water, the ions Na plus and Cl minus will separate. They will dissociate in the solution to form Na plus ions. So Na plus AQ plus Cl minus AQ. And this colorless solution will have a pH of 7. Okay, so that is a neutral salt. The next one, if we move one along, magnesium chloride. Okay, so again, we have an ionic compound. Magnesium chloride will also dissolve in water, a very similar process to sodium chloride. It's a white solid. It will dissolve and disappear as it dissolves in the water. But in this case, it's not going to have a pH of exactly 7. It's going to be very close. It forms a pH of about 6.5. So in the case of magnesium chloride, there is actually a very slight reaction with water. And remember, that reaction with water is referred to as hydrolysis. But it is a very, very slight reaction. Okay, so generally, we will just describe that process as dissolving, and you can represent it as we did for sodium chloride. So it will just be MgCl2 plus AQ forms Mg2 plus in solution plus 2 Cl minus ions in solution. Aluminium chloride is the first chloride where we will actually make some special observations, because although it will dissolve in the water, there will be a greater degree of hydrolysis also taking place. Okay, so hydrolysis referring to a reaction with water. And in this reaction, there will be some HCl gas, hydrogen chloride gas, being produced, and this will actually also be observed as misty or steamy fumes. And for all the remaining non-metal chlorides, so the silicon tetrachloride and the phosphorus pentachloride, there's going to be a violent reaction with water, okay, which is very exothermic, also referred to as hydrolysis reactions. And both of those reactions will produce hydrogen chloride gas, which you'll observe as steamy fumes. In the slides to follow, I will show some short video clips of these hydrolysis reactions, just to give a better idea of these observations referred to on this page. We know that electronegativity increases across periods, and it will be the same for period 3. So if we go back to sodium chloride and magnesium chloride, so both those chlorides are ionic compounds, because there's quite a big difference between the electronegativity of the chlorine, which is quite far to the right, compared to the sodium and magnesium, which are quite far to the left-hand side of the period. So we've got a high electronegativity versus a low one for sodium and magnesium. So chlorine is actually able to take possession of the electrons completely. There's going to be a transfer of electron from sodium to chlorine, or from magnesium to chlorine, to form the corresponding chloride ions and sodium and magnesium ions. As you move further across, though, there's going to be a smaller difference in electronegativity, and when we get to aluminium chloride for the first time, we start to see more of a covalent character as well. Okay, so there's going to be more sharing of electrons and not really a transfer of electrons. So although aluminium chloride is often indicated as AlCl3, aluminium trichloride, we know that 2 of those units combine to form dimers. Okay, so dimer referring to 2 of those units combining to form Al2Cl6. And we have looked at the dot and cross diagrams for those dimers, and it's important you practice how to draw this. Okay, they do ask it quite often. So make sure you know where to draw the 2 dative covalent bonds and then all of the other normal covalent bonds. If they don't ask for a dot and cross diagram specifically, okay, then you perfectly fine to give a diagram like this one, where we show the dative covalent bond using arrows and just instead of the single lines to represent single covalent bonds. Please just remember that the arrow is in the direction, okay, it shows where the 2 electrons come from. So in this case, it shows that this chlorine atom is giving both of the electrons in this dative covalent bond. And in this dative covalent bond, both electrons, okay, come from this chlorine atom. So when we consider the reaction of aluminium chloride with water, yes, it will dissolve to a certain extent, like the sodium chloride and magnesium chloride, but to a certain degree there will also be hydrolysis taking place, so an actual reaction with water where some hydrogen chloride gas will be produced. But we will look at the equations to represent those changes on the next slide, and I'll also show a short video clip with some observations. So when we have aluminium chloride added to water, so first of all we can consider just the dissolving process. So aluminium chloride, aluminium trichloride will split into aluminium 3+ ions, and there will be chloride ions in solution as well. Okay, so 3 chloride ions for every one of those aluminium trichloride units. But aluminium 3+ ions form what is known as a complex ion with water. So each aluminium ion will be surrounded by 6 water molecules, okay, to form a complex ion. And we'll cover these complex ions in a lot of detail next year. So a lot of the information on this slide you actually don't need to remember for this year, except the final equation. But I don't want to just give you the equation and not explain where it comes from. So the aluminium 3+ ion will combine with 6 water molecules to form a complex ion, and that complex ion can be shown as aluminium, and then in brackets H2O with a little 6. And overall there will be a charge on this complex ion because water molecules are neutral. Aluminium, as we can see here, has got a 3+ charge. So if we combine 6 neutral molecules to an ion with a charge of 3+, the overall charge will still be 3+. So this complex ion will have a charge of 3+, and I can show that by putting the overall formula in square brackets, and then outside of the brackets I have that 3+ charge. As a 3-dimensional diagram, this complex ion will look something like this. We're going to have aluminium as our central ion, and then there's going to be a octahedral arrangement of these water molecules around this central aluminium ion. So I can show that as follows. So I'm going to have a square planar arrangement first of all. So 4 water molecules kind of in the same plane. So let's say 2 of them going into the screen, 2 of them coming out of the screen. So this will be water molecules, and I'm writing it as OH2 just to show that it is the O that is bonded to the aluminium that forms a bond with that aluminium ion, and it actually forms a dative covalent bond. One of the lone pairs on the oxygen is used to form a bond with that central aluminium ion. But so far I've only shown 4 of the water molecules, and then in the plane of the screen up and down I'm going to have another water molecule going up. Okay, so H2O and H2O going down as well. So that's my octahedral arrangement of this complex ion. But I'm showing you this 3-dimensional arrangement just to get to the next point. These water molecules, now that they've formed these dative covalent bonds with a central metal ion, can actually act as acids. So it is possible for one of these water molecules, and I'm going to take this one, to donate an H+, okay, to act as an acid, as a proton donor. And when that happens, what is going to happen? So H2O, if we take away one of the H's, okay, and effectively if we lose a proton, we're going to be left with a negative charge. So that will then be OH minus, okay, after donating that proton. And this proton can then be obviously taken up by something else. And in the solution, we have these chloride ions in solution, and the H+ ion can combine with the chlorine to form HCl. And the hydrogen chloride formed will be observed as steamy fumes or misty fumes. So I just wanted to show you where the HCl comes from. All of this is way beyond the scope of the grade 11 syllabus. As I said, only the overall equation, which I'll give to you in a minute, is important. But anyway, in terms of observations, we're going to look at that short video clip. But in terms of the acidity, we're going to form an acidic solution because of the production of hydrogen chloride, or HCl. And the HCl gas will be observed as steamy fumes or misty fumes. So last thing before we look at the observations on that video. So this is before one of the water molecules donated an H+. What will it look like afterwards? So we still have the aluminium central metal ion. Instead of having 6 water molecules, we now only have 5. Okay, so we have 5 H2O molecules, and one of those water molecules formed an OH. Okay, so that will be the new formula here. But what is the charge on this complex ion? OH minus and Al3 plus, so 3 plus minus 1, so that will have an overall charge of 2 plus. So this is an important formula to remember when they ask you to give the equation or the product formed when aluminium chloride reacts with water. So in this video clip, we will look at the reaction between aluminium chloride, which is kind of a light yellow solid. So that would be the aluminium chloride. Don't worry too much about the concentrated ammonia added to this watch glass here. It's just something that we add to test for HCl gas. But anyway, when water is added to the aluminium chloride, you can see misty fumes or steamy fumes, and that's as a result of the production of HCl gas. So this reaction, because it produces HCl gas and there's a clear reaction between the aluminium chloride and the water, can be described as a hydrolysis reaction. It is very exothermic. It gives out a lot of heat, and if we add a large excess of water, that solid aluminium chloride crystals will eventually disappear completely. The pH of the resultant solution, will it be acidic or will it be alkaline? It will definitely be acidic, because as we've seen, some of those water molecules can donate H+ ions or protons and act as acids, so that will decrease the pH of the resultant solution. But in terms of observations, the white or misty steamy fumes of HCl or hydrogen chloride, the solid will eventually disappear, and we're going to observe heat being given off because it's an exothermic reaction. It can be described as hydrolysis, and it is quite a vigorous reaction as well. The following is not really important, but just for the sake of clarity, the ammonia that they refer to here, why do they add some ammonia solution to that watch glass? It's because it's a common test for HCl, because when NH3 combines with HCl, so ammonia gas plus HCl gas, it's going to form the resultant salt ammonium chloride, NH4Cl, because HCl will act as an acid. It's going to donate an H plus to the ammonia molecule to form the ammonium ion, NH4 plus, which combines with the Cl minus to form ammonium chloride, which is a white solid. And that white solid will be observed as white clouds. So just a test for the presence of HCl. Another way to test for the HCl, of course, you can use damp blue litmus paper, which will change to a red color. The overall equation then, aluminium chloride plus water will form this complex ion where one of the water molecules has donated an H plus or a proton, and that proton can potentially combine with some chloride ions to form HCl, which we observe as the white steamy fumes. In this first clip, we will look at the reaction between silicon tetrachloride and water. First of all, please note the appearance of the SiCl4. It is a colorless liquid. It is a liquid at room temperature. If we add damp blue litmus paper into this container, you can see it's being decolorized to a red color, and that's because the silicon tetrachloride will react with some water in the atmosphere to produce HCl, and the HCl will then decolorize that litmus paper. If we add some water to the actual silicon tetrachloride and go beyond the reaction of the silicon tetrachloride and only the atmospheric water, you'll see that there's going to be a much more vigorous reaction, producing greater amounts of HCl, and therefore there's going to be more of these steamy fumes being produced, and that's what you can see here at the moment. But remember, they have added some ammonia here as well, so some of this white smoke that you're seeing here is actually the ammonium chloride produced via the reaction of HCl with NH3. So in terms of observations for this reaction, the white steamy fumes of HCl, once again, because the type of reaction is hydrolysis, and it involves the reaction of these covalent chlorides with water. So when it's ionic, we generally have only dissolving taking place. As soon as we go from ionic to some covalent character, we're going to have some hydrolysis. And in the case of these non-metal chlorides, which have a very high degree of covalent character, it is quite a vigorous hydrolysis reaction taking place. So very exothermic white fumes being produced in this reaction as well. So this is the overall reaction equation for that reaction. It is silicon tetrachloride, a liquid at room temperature. It's a colorless liquid because we only have weak intermolecular forces between the silicon tetrachloride molecules. It's a simple molecular structure reacting with liquid water. We produce HCl, which we observe as the white steamy fumes, and in addition to that we also produce silicon dioxide. And we know that silicon dioxide is very, very insoluble in water. So if we added an excess water to the silicon tetrachloride, what would you observe? Would the silicon dioxide ever dissolve? No, you're going to observe a white solid in that solution as well. So the two observations will be the white steamy fumes, and there's going to be a white solid also observed, or white PPT, as a result of the silicon dioxide produced. This is the last one of these reactions of the chlorides with water, and this last one is PCl5, so phosphorus pentachloride. At room temperature it is a white solid. That's important. Know that PCl5 is a white solid at room temperature, and let's see what happens when we add water to this compound. But let's see if we if we can make some predictions. PCl5, what type of bonding involved in that molecule between phosphorus and chlorine? Two nonmetals, so it's covalent. So a covalent compound reacting with water, so we're going to expect hydrolysis to take place. Hydrolysis reactions are often vigorous and exothermic, but let's look at what happens. Okay, so that's our solid PCl5. Some water added, vigorous reaction. You can see a lot of white fumes being produced, or steamy fumes, and that's as a result of the production of HCl gas. And in addition to hydrogen chloride gas, this solution will be highly acidic because of the production of this acid, phosphoric acid. And remember the systematic name, we have to give the oxidation state of the phosphorus in that acid. So if we work that out, we'll get to the following. So we know that PO4, the phosphate ion, overall has got a charge of 3-, so the oxidation numbers must add up to -3. Oxygen is -2, so 4 times -2 is -8. So what must phosphorus be to give us the answer of -3? It means phosphorus must be +5. So therefore that acid is known as phosphoric acid. But specifically, because we get different types of phosphoric acids, we can have H3PO3 as well. So this is phosphoric 5 acid. So 5 Roman numeral in brackets acid. So it's going to be a very acidic solution. The pH will be anything around pH of 1 and 2, obviously depending on the concentration, but it is a highly acidic solution. Let's look at the overall equation for that reaction between the phosphorus pentachloride, which is a solid at room temperature, and liquid water. It produces HCl gas, the white fumes or steamy fumes, and also phosphoric 5 acid. So that's important. Please just note, in the initial slides there was a typo. It's not H3PO3, it's H3PO4. Okay, so please just change that little subscript in your notes.